Chapter 20 deals with radioactivity and nuclear chemistry. This is a powerful topic that has many applications, from producing different elements in the stars, as shown in the image on the left, or harnessing the power of fission in order to produce energy in nuclear power plants. We can also harness radioactivity to do diagnostic tests for medicine. So applications, there's lots of different applications for nuclear chemistry. And the one that most people think about is nuclear bombs or nuclear energy, but there are lots of other applications that we can do and use. So one is, it gets used in the medical field quite a lot. So they can be treatments, they can be diagnostic tools that are used using the detection of nuclear particles. And the reason for this is because they pass through the body and tissue very easily. We can also look at dating things through the natural radioactive decay of different elements, and so we can look at dating fossils and rocks and artifacts. We can also look at fission, nuclear fission, which is what we use for electricity generation, and also nuclear weapons. And at the end of the chapter, we'll also look at like food preservation with nuclear reactions. So let's start with a few different types of radioactive decay. So when we have a nuclear reaction, we get different types of radiation that comes from that. And so radiation, or being radioactive, it means that we're emitting radiation. Okay, high energy electromagnetic radiation that comes from a reaction in the nucleus of certain atoms. And so the first particle we're going to look at, and we'll look at each of these in more depth, but the first particle is alpha particles, or alpha rays. And these have a charge of a +2 and a mass of 4 atomic mass units. And you might think, that sounds familiar, right? +2, 4 atomic mass units. That sounds a lot like helium. Well, it is helium with no electrons. And so this is a helium nucleus, is an alpha particle. And these alpha particles are what led to the identification of the nucleus of an atom. So this is what Rutherford used in his experiments to find that the nucleus of an atom was very tiny and in the center. We also have beta rays, or beta particles, and they have a charge of -1 with no mass. And again, this sounds kind of familiar, right? This sounds like an electron, and it is. They're like an electron. They're high energy. We'll talk a little bit more about beta particles in a minute. Gamma rays are a type of light energy, so they're not a particle like alpha and beta, but they're a form of electromagnetic radiation. And so these are the shortest wavelength, highest energy in our electromagnetic spectrum. We do have other types of radioactive decay. So we have positrons, which are kind of like positively charged electrons, so antimatter. And then some other nuclei, they'll undergo electron capture. So they'll actually grab an electron out of the cloud and pull it into the nucleus and incorporate it into the nucleus. So one of the first topics that we need to remember from general chemistry in order to understand nuclear chemistry is isotopic notation. And this is where we write the chemical symbol. We've got the mass number above and the atomic number below to the left of our chemical symbol. And so if we were going to write hydrogen, we'd write our elemental symbol or chemical symbol of H for hydrogen. The atomic number is the number of protons. The mass number is protons plus neutrons. And so if we were talking about hydrogen, we would look at our periodic table to find our atomic symbol, which is 1. And then our mass number depends on the type of isotope that it is. So if we were going to have deuterium, we would put a 2 for our mass number. So deuterium is a hydrogen that has 1 proton and 1 neutron. Okay, these are called nuclides. So the nucleus is what we call a nuclide, and each nuclide we define using the mass number and the atomic number. So when we're writing, there's different atomic symbols that we use. If we're talking about a proton, we can represent it as P for proton, which have a positive charge, and we can either write it as the hydrogen symbol or as P for proton. Remember, neutrons are neutral, and so there are no protons, but neutrons still have a mass of 1. Electrons are like the opposite of a proton. So that is why we end up with a negative sign for the protons to represent the electrons, because it is like the opposite of a proton. And it has no mass, and so that's why we end up with a 0 for our mass number. Now our alpha particles, we can either represent them with an alpha or with the atomic symbol helium. Beta, again, can either be a beta symbol or an electron. And then positrons are a positively charged electron, and so we can either write it as a beta or as an E with a positive charge, showing that it is a positron. When we write nuclear equations, we need to make sure that we include the atomic numbers and the mass numbers, because those are conserved on the left side of the reaction and the right side. So we are no longer balancing types of atoms. We are now balancing atomic numbers and mass numbers. So we have on the reactant side what we call a parent nuclide. Okay, so this is where we're starting, the initial element that we're starting with. On the product side, it is called a daughter nuclide, and this is what we're ending up with. And so, again, our elements are not conserved. Okay, we're transmuting, we're making different elements. But you will notice that if we look at the mass number, we're starting with 238, and we're ending up with 234 plus 4 from our alpha particle. Okay. So they both still equal each other from the left side to the right side. If we look at for the mass number, if we look at our atomic number, we're starting with 92. and we're ending up with 90 plus 2. So our atomic number is conserved from the left side to the right side. And this is how we balance our nuclear equations. So we usually know what the parent nuclide is. We know the emission or the particle that is given off, and we can calculate what the daughter would be. An example of alpha decay is the decay of uranium-238 into thorium with an alpha particle. So the alpha particle, remember, is composed of 2 protons and 2 neutrons. It is the most ionizing form of radiation. So this means that it can interact and damage molecules by reacting chemically with them. So if it gets into your cells, these particles have the greatest chance of damaging your DNA and potentially leading to cell death or abnormal growth of cells through damage to the DNA. However, because these are such large particles, they have the least amount of penetrating power. So they can be blocked by a sheet of paper, they can be blocked by cloth or clothing, and even the air. Beta decay is where an electron is emitted from the nucleus, and so an example of that is carbon-14, where we have carbon-14 that once it undergoes beta decay, the removal of that electron, which is like the opposite of a proton, we decrease our atomic number by 1, we end up with nitrogen. So this is about 10 times more penetrating than an alpha particle, but it is about half as ionizing. So it causes less damage, but it can travel further into the body. Gamma emission, remember these are not particles, these are high energy electromagnetic waves. And so there is no change in composition of the nucleus, so the atomic number and the mass number stay the same. It is the least ionizing, but it can make it through the largest distance or the thickest substances like lead. And we'll talk a little bit more about that on the next slide. So this doesn't change our nucleus at all, but it does generally happen in concert or at the same time as another type of particle decay. And so we do end up, like our example of the alpha particle, here we have uranium-238, which is uranium used in nuclear weapons or in energy production, producing thorium, an alpha particle, and also a gamma ray. So let's write the nuclear equation for the alpha decay of radium-244. So when you see the dash with a number after an element, that is our mass number. So we know that our mass number for our radium is 244. We can go to the periodic table, find that it has 88 protons. So we are trying to figure out what the daughter nuclide is, what its mass number is, and what its atomic number. We know because it undergoes alpha decay that we are going to end up with helium. We've got 2 protons and also 2 neutrons, which gives us a mass number of 4. So we can subtract from our radium to find our daughter nuclide. So we know that our alpha particle has a mass number of 4, so if we take 224 minus 4, we end up with a mass number of 220. If we look at our atomic number, we have 88, and our alpha particle has 2, so we take 88 minus 2, we end up with 86. And if we want to figure out which element that is, we can go to the periodic table, look up the element with a mass number of 86, and we see that it is radon. Now you may have heard of radon because some people have radon detectors in their basement, and this is because it is a naturally occurring product from the decay of radioactive elements in some locations around the country. Here's an example. So write the nuclear equation for the alpha decay of polonium-216. So we know 216 is our mass number for polonium. If we go to the periodic table, we see that it has an atomic number of 84. Again, this is an alpha decay, so we're going to have helium that is given off, and we want to figure out what our daughter nuclide is. So we would take 216 minus 4, so we end up with a mass number of 212. We would take 84 minus 2, and we would end up with an atomic number of 82. We go to our periodic table, and we would see that we would have lead. So lead would be our daughter nuclide from the alpha decay of polonium. So when we were talking about penetrating power, this is just showing you if we're looking at lead, if we have alpha decay, an alpha particle can be stopped by 0.01 millimeters of lead, which is a fairly thin piece of lead. If we go up to a beta particle, now we're up to 1 millimeter, and gamma, we can go through 100 millimeters of lead. So the larger the particle, the easier it is to stop. So here is a table that summarizes the three radioactive decays we've already talked about, alpha, beta, and gamma. We've added in positron emission. And so positron emission is when we have an antiparticle of an electron. It's similar to the beta particle in their ionizing and penetrating ability. And positrons result from a proton changing into a neutron. So if we get a proton that changes to a neutron, it gives off a positron. We also have electron capture. So electron capture is where it actually pulls an electron from an inner orbital into the nucleus. And there is no emission, but the atom does change, right? So the type of element changes when we have electron capture. And this is where we take a proton, we combine it with the electron, and it forms a neutron. So let's try an example of writing nuclear equations for each type of decay. So now we're going to write a beta particle decay, a positron emission, and an electron capture. pause the video, see if you can write these equations. So let's start with a beta decay of berkelium. So we're told that berkelium has a mass number of 249. If we look on the periodic table, we have 97 protons. If it is a beta decay, that means that we're giving off an electron. And so our mass number is going to remain the same because we have 0 for a mass number on our electron. So we're still going to have 249 for our mass number. Our atomic number is going to increase by 1. So we're going to get 98. If we look on the periodic table, atomic number 98 is californium. So with our beta decay, it increases by one atomic mass number. If we look at B, positron emission, so we're going to start with our oxygen 15, which has 8 protons. Again, this is positron emission, so positron is like an anti-electron. It's got +1 charge. So our mass number is going to remain the same because our electron has no mass. Our atomic number is going to 8 minus 1, so we're going to decrease by 1 atomic mass number. And so we end up with 7. If we look on the periodic table, that would be a nitrogen. Electron capture, so we have iodine 111, which has 53 protons. It's electron capture, so this goes on the reactant side. And so our mass number again does not change, but our number of protons decreases by 1. So we have 52 protons. If we look on the periodic table, this is tellurium.